trains.
Since the invention of the wheel, man has been searching for faster, cheaper, and more efficient means by which to travel. Today, we look to man's most recent development in the wheel, so developed in fact, it no longer exists. Train and rail development began in the early 19th century with the introduction of steam-powered locomotives. Then came diesel-powered engines, then the wide variety of electrically driven trains. But whilst trains have certainly advanced in speed and efficiency, their development is limited by friction between wheels and rails. The Maglev train, first conceived by German inventor Alfred Zieden in the early 20th century, offers the solution to this mechanical limit. There are two primary Maglev technologies, electromagnetic and electrodynamic suspension. Electromagnetic suspension is a German system that uses supporting electromagnets on the train's body, directed upwards towards a ferromagnetic guideway. The attractive magnetic force between these components lifts the train to heights of up to 15 centimeters above the track. Guidance magnets on the inside of the train's structure are used to maintain horizontal stability. Propulsion is provided by a long stator linear motor. To understand this, imagine an electric motor whose stator is cut open and stretched along the underside of the guideway. This stator consists of three-phase motor windings, which when supplied with an alternating current produce a travelling electromagnetic field that excites the supporting electromagnets on the train and generates propulsion. The speed of the train is continuously regulated by varying the frequency of this alternating current. In electrodynamic suspension, a system invented by the Japanese, there is a series of inactive figure-of-eight coils within the guideway walls. Supercooled, superconducting magnets are located within the train, which provide a very powerful magnetic force due to their negligible resistance and are positioned so they lie below the centre of these figure-of-eight coils. When the train moves, the coils experience changing flux, and thus, by Lenz's law, an opposing and attracting magnetic field is induced in the lower and upper half of the figure-of-eight respectively, and the train levitates. This is why the system is termed electrodynamic. Without actually moving in the first place, there would be no induced currents in the figure-of-eight coils, and the train would not levitate, unlike the EMS train, which levitates regardless of motion. EDS trains therefore have wheels or some other form of landing gear in order to support the weight of the train until it reaches a speed to sustain levitation. Similar to EMS, propulsion for EDS works using a linear motor. By passing an alternating current through the propulsion coils installed on either side of the guideway, magnetic forces with alternating north and south poles are produced. The train is propelled by these simultaneous attractive and repulsive forces. EMS trains do not use superconducting magnets, which means they do not require the expensive cooling procedures to keep these magnets at superconducting temperatures. Also, this makes it safer for passengers with pacemakers or magnetic data storage. Unlike EMS trains, the horizontal positioning of EDS trains is maintained without any active control. When the train moves off centre to one side, an electric current is induced in the figure-of-eight coils which, by Lenz's law, works to oppose the change and return the train to centre. Despite these differences, both methods use technology that shows great future potential. A lack of noise pollution, all-weather operation, no need for overhead wiring, and a general increase in efficiency are only several of the Maglev's numerous benefits. Most significantly are the express speeds it can achieve due to its frictionless travel. In 2003, a Japanese EDS Maglev was recorded travelling at speeds up to 581 km per hour. The only current downside to the technology in general is the expensive construction of train and guidance rails. With further research and development and a more widespread acceptance across the world's major cities, the technology yields great promise for the future. It may well rival the significance of the commercial aviation industry, and indeed revolutionise travel of the increasingly globalised 21st century.